electric field potential and the derivative of an integral. In fact, when we compute the electric field, we use Coulomb's law. However, electric field and electrostatic force, both of them are vector quantity. Although in principle we can compute the electric field and electrostatic force directly from the definition provided by the Coulomb's law, it is more convenient to make use of the electrostatic potential because the electrostatic potential is a scalar field. Is much easier than to compute rather than the electric field, vector field. However, at the end of the calculation, we derive the electric field out of the potential. That is carried out by taking the derivative. So potential calculation of potential involves a definite integral. And then calculation of the electric field from the potential involves the derivative. In high school, we learned how to compute this definite integral whose upper and lower limit depends on the variable x. And actually, if you take the derivative with respect to x, this is nothing but the function itself. However, in reality, in physics problem, uh, life is not that easy. We have some function of x instead of x. So we need to apply the chain rule again. So we review how to do this computation and apply it to the computation of the electric field from the potential. Okay. Verify the formula. I hope everybody knows this, but we first introduce a primitive function, or we say is an indefinite integral, where I did not substitute any upper limit or lower limit. So this is a function called capital F, and we have an uncertainty. We are free to add any constant, integral constant can be added, whatever value it may be. And then we have upper limit, lower limit. In that case, this one is replaced with f of a subtracted by f of b. Okay, because this is a pure number, it is not a variable. If you take the derivative of this fixed upper limit and lower limit, if I take the derivative, it is 0 because it is a constant. So next step, we replace this one with x. And for convenience, we choose arbitrary constant a. Then this guy is f of x subtracted by f of a. Okay? And then we take the derivative. What's that? We do not have c anymore. By definition, this is by definition, derivative of the primitive function is the integrand of this integral. Okay, that's it. So this is what we just have done. Next step, what happens if the upper limit is not simple x, but a function of x, and I take the derivative? Then the answer is this. Let's prove this. We recall that Any indefinite integer is of a small f is expressed in terms of capital F. And by definition, we take the derivative, then the answer is this. We just have shown that if this is any kind of constant and x, then this f of x can be expressed in this manner. F of x equals derivative of. So we usually distinguish this one by attaching prime because it is a variable, and this is a dummy variable that is integrated out. All right. However, unfortunately, what we have is not the same x. Instead, we have g of x. So we take the derivative with respect to x, but this is a function. I have to substitute this one into the argument. So f of g of x subtracted by f of a. We take the derivative of this, right? Derivative of this. So I copy this result in here. We take the derivative. This is a function of a function. Implicit function derivative can be done by using chain rule. First, take the derivative with respect to this full expression. So, derivative of capital F with respect to g, and then we have to take the derivative of g with respect to x. As a result, this one is nothing but the original function f with the argument. Instead of x, we have g of x as an argument. And then we take the derivative of g with respect to x. Using this formula, we can compute the electric field very, very easily. In addition, in case we have additional dependence on x as a function in the lower limit as well as the upper limit, then the same style of computation is given in here. Okay, this is g and this is h, so h derivative. Okay, so it's very simple to find the answer. Next step, potential energy of a conservative force is defined by, yes, this is a reference value, and from a point to an arbitrary field point, and this field point is the argument of the potential. And we use the field, it is not mathematical field that is defined by algebra, but physical field is a function of position. So this value varies depending on the position. In addition, a conservative force has an integer that is independent of the path. So the value of this integer depends only on the endpoints. So we can choose the arbitrary path from A to B. So whatever path you may choose, if you're clever, you might want to choose the simplest path along which the integral becomes compact. So why don't we choose these 3 points? So we can draw a box. Initial point whose Cartesian coordinates are A1, A2, A3. Our final point is x, whose Cartesian coordinates are x1, x2, and x3. So I'd like to choose the path from here to there. I change only third component. So this is the path I have chosen. This is the first path. This is A1, A2, and X3. So these two values are constant, but I vary Z component from A3 to X3. And then next step is to keep this X3 and A1 the same. And we vary A2 to X2. If we choose the E1, E2, and E3, then this is X2, this direction. So inside, oh, sorry about that. A This is the first path, A1, A2, A3, and this is A1, A2, X3, and then this path, A1, X2, X3. And then finally, we choose this path. So vary A1 to X1. Then this work can be computed in a very simple manner. First path, this path involves the dx3 integral. Z component integral contributes only this one. First path, A1, A2, A3. I changed x3 only. And because they are integrated over this path, we use primed variable for this. And then next step is to change the y component. And this integral involves x2 integral. So x2 prime integral. So, and in this case, x2 dependence, scalar product, only f2 contributes, and the starting point is a1, a2, x3, a1, a2, x3. The end point is a1, x2, x3. And finally, this is the last path along the x-axis, dx1 prime. So dx1 prime, it collects the first component, the first computation component only. This is this, dx1 integral from a1, x2, x3, a1, x2, x3, to the end point, that is x1, x2, x3, x1, x2, x3. Okay, using this expression, I can take the partial derivative with respect to x1. First of all, x1 dependence appears only in this term. There is x1 only in the first term. The second and third integral does not have any information about x1. Therefore, the partial derivative with respect to x1 is not vanishing only for the first term. And these two will vanish. As you know, our derivative rule, in here we have a simple dependence on x. Therefore, this derivative is nothing but the first component of the force, and we have negative sign. So in here, I have to put the negative sign. So why don't we, let me correct this one later. This one should be erased. Okay, this is not minus, it is a positive. And then finally, what we obtain in here is a derivative of u. Derivative of U equals minus F1, right? That is correct. And in a similar manner, X2 dependence appears in here and there. We can finally make you simplify the whole results, but we can choose the another path. This is the most convenient for the derivative of x1, but in case if you want to find the derivative of x2, simplest path is to let the x2 appears in the last stage only. That means let this one appears following this path. So keep these paths. In that case, change in x1 appears only in the last stage. So using this method, I can compute the f of 2 and f of 3. Finally, the force can be computed from the potential energy by taking the negative gradient.